Hello, I'm Siddhant. I'm a master's student in India, and it's good to be here at Daylife to present some of the work that I did as an undergrad. Uh, and it's a lot of chemistry. I'm not sure how many of you are chemists or biochemists, but it's always good to know new things. So the title of my presentation is Discovering Autocatalytic Networks and Prebiotic Chemical Reaction Networks. That's a big mouthful title. But what this work is going to describe is building a just generalized computational workflow where you expand reactions, chemical reactions, and then in that expanded reaction network, find emergent behaviors, autocatalytic cycles, phase flux flows, as well as calculate descriptors of all of these molecules. There's a lot of network science, and that's why it's interesting. So I just have to, because I can't see the screen, I have to go back. Why it's good for me to explore explain chemical reaction networks because a lot of people here are not chemists or maybe they're chemists. What we want to do is we want to look at pre-biological chemistry. So chemistry that was before biology, in the early origins of life, phase phenomena. And we want to encompass it as like a certain chemical reaction will be biochemistry, then doing a thermodynamic predictions, predicting the reaction paths, getting autocatalytic data, and then finally using tools in cheminformatics, the network theory for visualization and characterization. So let's talk about graphs. Here's my collaborator, Jacob Lyden's, and also from Denmark, Odense. I think it's somewhere far away from Denmark, from Copenhagen, but I can still visit. So how do we want to represent these chemical reactions in a way that the computer or the program understands? Is that we use a tool called mod, where we write these rules to represent a chemical reaction. There is a rule that will someone raise that hand, but that's fine. So there is a rule because my rule is somebody can write in the chat for Martin.
1 second.
Yeah, it's fine.
There is no rising hands now.
So now my rule is visualized. So we how do we write these rules in graph theory? Is that the way you represent it's a carbon hydrogen bond. I'm breaking this bond to form an atom. So this is where my chemical entity becomes important. You know the chemistry behind it. We go and write these in the graph markup language in a way that you give them node IDs and then you play with these node IDs to get you a reaction product. But it's a simple example. Now I can do it with very standard organic chemistry reactions that I will apply to expand and generate my network. So yeah, how do we do this? How does this work? So what you do is you load these initial reactants. Reactants are the chemical products. So for example, I'll take an example of glucose in water. That is one of the reactions that we studied. So I take glucose in water and I load these reaction tools that I've written in graph theory language to apply on this glucose water. And I apply these rules and I get the reactions of glucose to given products. What I do, I run an iterative cycle. I take the products of the first round, get it back, then apply the same rules. So it forms generation 1, generation 2, and for the whole generation. And if you form returns, it's going on and on. Now we also apply some filters to keep out bad structures. Bad structures in chemistry where we don't want to allow such structures like 3 rings or like 7 rings that are just not filterable in nature. And then we also apply thermodynamics to constrain our networks. So we get the clean products and then we take these clean products for generating and optimizing our networks and visualizing it and doing a lot of discrete analysis and furthermore looking at our analysis. So this is the phenomenon where you define the rules, you define the molecules, you expand the network you want, remove the nodes that you don't want, you add other constraints such as thermodynamics, and then you evaluate with literature-based data, with mass spectrometric data, because it is always good to evaluate your computation models with experiments just to get a ground truth. Then we export it to Neo4j, which is a graph theory-based database to explore autocatalytic cycles and relationships and look at cycle numbers or catalytic lengths. And yeah, just to give you an exact idea about the product complexity, where we have 2 kinds of reactions, that reaction of glucose, which was published in 2022, and the formos reaction, which is just about to get published. So here you can see in generation 0, you have so less number of species which are your initial reactants. But as you move on and on, the amount of complexity increases with the amount of cumulative edge and reaction edge is also very increasing. So the computational time varies a lot. Due to the interest of our computational time and our machine only could run certain things or certain number of reactions, the generation 6 and generation 5 are our bottlenecks. But if we had access to a powerful system, we could have explored a lot more chemical space and you have utilized a lot more. So how does this reaction do with statistics? I'm not sure if it's as important, but it's a pretty picture. So it's always good to do pretty pictures. So we also looked at how, so these are general organic chemistry reactions. You have these reactions in general chemistry and you know it by reality. So we wanted to look at how are these reactions spread across a chemical space or genetic chemical space. And then we also calculated the free energy or delta G or thermodynamics at particular pHs using equilibrium, which is again a semi-empirical method that you can calculate gives free energy for biochemical or chemical reactions. We calculated at 2, 7, and 10, and we wanted to look at how are these reactions changing at these, how the free energy of change changing for these reactions at different pHs, thus to get a better idea about how these reactions were in the evolution of life. So now, since we did computation, we also wanted to identify if what our model is predicting is actually true or not. Otherwise, it's garbage in garbage. So we took this paper by Yang and Montgomery in 1996, and we matched 96% of the molecules for a glucose network, which is true that the model is working. And these people have done it with gas chromatography, mass spectra, and things like that. Now, this is a recent paper in 2020 where our molecules, our computational model matched 100% of the molecules in focus. That's good enough. That means it's working, and now we can move forward for analyzing these things. We also compared the mass spectra data for the lab molecules, which were done at National Mag Lab in Florida. I'm not showing that data due to interest of time. But we now, I think a lot of people are here doing networks. So we also calculated the in degree and out degree for this statistics for both the glucose and formose chemical reaction networks. And we wanted to look at which of these reaction products have more of an in degree or out degree. And we can have certain statistics like what are these molecules that are more common, as in if I define it in respect of integrity and aldehyde for both of these characteristics. You know, water is very connected. That was obvious. But we could also see some of the other molecules that were expected or not so much expected using these tools and techniques. Now, one of our reviewers also asked, like, you did glucose or you did simple small molecules in organic chemistry, but can you also add mineral ions to these networks and expand or constrain the networks based on that? Which is true. We added iron to our iron forms network, and then we defined our graph rules to include iron as well. You can use other methods too, which is very important in the course of evolution of life. So we were able to add iron, and then we were able to constrain, or we were able to show that iron catalyzes a lot of reactions, but the overall complexity might increase by utilizing metals. Now, since I will be running out of time, I just want to touch on this topic of autocatalysis. Autocatalysis is a wonderful phenomenon which is involved in biochemistry, chemistry, and cytobiology. So we wanted to look at and identify the autocatalytic motives using graph theory in our chemical reaction network. So here are some, there's autocatalytic motives, or some of them that I'm showing you for a glucose chemical reaction network. One, we looked at certain of these cycles that were presented in literature, and we were able to go back in the lab at University of New South Wales to verify some of these cycles that are more capable. We have the cycle frequencies, and we also calculated covariance. We can give you how many of these cycle lengths are spontaneous or non-spontaneous based on spontaneity, and we get the delta G values out. It's really important for this kind of work is really important for experimentalists to design their experiments when they're going in the lab. And same goes for autocatalytic motives in formose. Since we are not discussing a lot of things here, it's just important that what we did differently in formose than glucose is to look at how are these cycles feeded? What are the feeders of these cycles? Is it a 1 feeder? Is it a 2 feeder? It's a 3 feeder? And then we look at the frequencies and cycle lengths of that. I think that will be the end of this book, and thank you. I'm happy to take questions from you.